Okay. So, question, you need one, Stella, too, because you came in. And Simeon, you need one too, don't you? Oh my goodness. Let's see here. 1, 2. Right. All right. Simeon. You. Okay. So the chain rule, we're going to be spending a few days here in this particular section. And the reason why is because it's kind of tricky to kind of get down, right? We have to like develop our sense for these kind of problems, and we'll be doing that through just, some practice and stuff like that. Okay, so I'll take you through the basic steps of the chain rule today, and then we'll, kind of continue practicing it for a few more days here. Okay, for those of you that are taking the PSATs on Wednesday, of course, there's not anything scheduled for us to learn that day, so we'll probably just make that day, for those of you that will be here, we'll probably just make that day like a, do your homework kind of day or something, get your homework done, or get caught up on homework kind of day or something like that. We won't do anything new on the PSAT day. Okay, but every other day, of course, we work on the chain rule here. So let's get into this right now, all right? So we're going to do a little bit of an exploration to kind of get a feel for what this chain rule is all about first, and then we'll, kind of discuss it. Kind of like what we did with the product rule and the quotient rule and stuff, okay? Kind of see it, and then, or see a need for it maybe, and then we'll go about it. All right, so first of all, when we go to find the derivative here of this function, right, we're going to use the basic power rule to find f prime of x, the first derivative, given that f of x is equal to x plus 3 quantity squared. Okay, so basic power rule, I'm going to draw a little line down here. So in other words, we're going to take that function f of x equal to x plus 3 quantity squared. Okay. And we're going to try and apply the basic power rule to that. So in other words, we're going to take the derivative, and we're going to take the exponent here 2, and normally what we do when we have an exponent of 2, we bring that 2 out front, right? Leave that x plus 3 alone, and then lower our power by 1. So it's 2 times the quantity x plus 3 to the 1 there. Or if we wanted to, we could then distribute the 2 and make it 2x plus 6, right? So that's what the directions kind of wanted us to do there. Okay. I'm going to put in quotes here, because that's kind of a new thing. We haven't really seen that. We haven't really done that, okay? Ordinarily, what would we do to take the derivative of this function? We need to multiply it out, right? Okay, what we've been doing is that we've taken the function f of x, and we've taken that x plus 3 squared, and said, okay, that's going to be, x plus 3 times x plus 3, and so it's going to be x squared plus 6x plus 9. Okay. And then we take the derivative, right? Then we take the derivative. And that's what we should do, but now we're going to learn the chain rule and see a different way. So the derivative here would be, well, what would the derivative of this be? 2x plus 6. Yeah, exactly right. 2x plus 6. Okay, and we can see that, they match up. Okay. So hopefully we can see the benefit here is that in this problem, we were able to take the derivative much faster, right? We didn't have to do that intermediate step of multiplying the x plus 3 times itself to get the x squared plus 6x plus 9 and then take the derivative. We were able to take the derivative as it was written. Right? Seemingly, we were able to take the derivative here as it was written using just our normal power rule. Right? We had something squared, and so what's the derivative of something squared? 2 times that something to the first power. So seemingly, we could just do that instead of multiplying it out first and then taking the derivative. Okay? This we know will always work because that's what we've been using. Right? This is new. Maybe it will always work, maybe it won't. So let's see what happens for the next one here. Okay, so now we got a slightly different function, but the same directions. Use the basic power rule to find g prime of x, given g of x is equal to 2x minus 1 to the second, and then multiply g of x out and differentiate. All right, so again, we'll take the derivative here. I'll rewrite g of x. So g of x is equal to the quantity 2x minus 1 squared. And again, we'll just use the power rule here. So I'll write g prime of x equals, okay, again, just using the power rule, we're going to bring that 2 out front. lower the power by 1, so it's 2 times 2x minus 1. Okay, and I'm going to put the g prime of x here in quotations, right? We don't know for sure that it's g prime of x, but we're going to say maybe it is. Okay, if I distribute this out, I get 4x minus 2. Okay, so you guys over here, go ahead, do it how we're supposed to do it over here. So do it how we're supposed to do it over here. So take like a second or two and do it how we're supposed to do it right there. Okay. Peyton, do you have an answer for us? It is 8x minus 4. Which is great news. We took the derivative there, but which is also bad news because what did work in that first step, right, they were exactly the same derivative, right? This problem being nicer because we could save ourselves having to square out the x plus 3 and just take the derivative as it was written. Here, it didn't quite match up, did it? Here we ended up with a 4x minus 2, right, when we tried to take the derivative using the power rule here, 2 out front, and then to the 2 times 2x minus 1 to the 1, and distribute the 2 there. We get 4x minus 2. Here we get 8x minus 4. But are these things as different as they look? No. So what could I do here to make this look more like this? Yeah, factor out a common factor of a 2, okay? And lo and behold, we end up with something that's pretty darn close, right? Pretty darn close. Here's the actual derivative, what we want it to be. Here's what the derivative actually is. Here's what we want it to be. Very close. They only differ by a factor of 2. So we'll kind of compare these two here, but they're not quite the same. So not quite the same. Here it was the same, so check. Put it like a check. Okay. All right. Let's go ahead and do the same thing here for number 3. All right, so number 3, again, same rule. We're going to use the basic power rule first, take the derivative of this, and then we'll actually multiply it out and take the derivative like we're supposed to here. So if we've got h of x, which is equal to the quantity 3x squared plus 1 squared, h prime of x, and again, I'm going to put that in quotes. This is what we kind of want it to be, want it to work out to be. We end up with 2 times the quantity 3x squared plus 1 to the 1. Okay, again, just using that power rule, using that basic power rule we've been using. We really would like it to be that, so we don't have to square out that 3x squared plus 1, so we can avoid it. Okay, and then you guys go ahead and take the derivative of the way we know we're supposed to. The way we're supposed to right over here. So go ahead and do that yourselves there. So, Carter, what'd you get for the derivative here?
36x cubed plus 12x.
There you go. Yep, 36x cubed plus 12x. Okay, 36x cubed plus 12x. And again, so if I distribute the 2 in this one here, we get 6x squared plus 2. And again, they look pretty different, but are they really that different? How could I get my actual derivative to look like what I want it to kind of look like there? What can we factor out here? Yeah, factor out a 6x, and I'm left behind with 6x squared plus 2. So again, we see what we were hoping, that our little shortcut for the derivative here, okay? We want that to work out, and it's pretty darn close, but now we're off by a 6x there, a 6x. Okay, which, let me do one more step here to kind of help make it maybe a little bit more obvious. If I take out, let me see here. If I take out one more thing, how did I want to fix this here? Well, all right. If I take a 2 out here, is that what I want to do? Yes. I take a 2 out here and leave it as 3x squared plus 1. And then I can take a 2 out here still. Which make it then 12x times 3x squared plus 1. Okay. So again, I factored the GCF out of here, and I factored the GCF out of there too. So, okay. So yeah. So again, these are pretty close. Pretty close. The only difference is that this has a 2 out front, this has 12x. Okay? So if I were to break that 12x up in a particular way here, make it maybe a little bit more obvious. So you can see that they only differ by a 6x, right? This one's got 2 times 3x squared plus 1. This has the 2, it has the 3x squared plus 1, but it's got another 6x in there for the actual derivative. So again, comparing this one to this one right here. Okay? They're not quite the same. Right? Likewise here, right? They weren't quite the same there. Okay, not quite the same. Alrighty. And so then the last one here, let's go ahead and do this one. So again, m of x is equal to that x cubed plus x quantity squared. Okay. And then we will take the derivative here. And again, taking it the way that we kind of want to take it, we'll bring that 2 out front. Okay, and lower the power by 1, like that. Okay. That's what we want the derivative to be. But then compare that to what it will actually be here. If we multiply out the m of x, it's going to be x to the 6th plus 2x to the 4th plus x squared. Okay. And then its derivative will be 6x to the 5th plus 8x to the 3rd plus 2x. Okay. Now, I'm going to factor this again, okay, just a little bit of a, just factor this out a little bit more here, just to kind of see. So if I factor out a 2x initially here, we'll be left with a 3x to the 4th plus 4x squared plus 1. And then this also further factors, okay? This also further factors here. So let me just show that to you here. Okay, and again, there's a reason for this. I know normally we don't do this, right? We're just kind of like, we took the derivative, it's done. But just to kind of see what's going on here, this further factors to 3x squared plus 1 times x squared plus 1. Let me factor out the GCF here too. It'll be 2x times x squared plus 1. So when I factor both, what we're kind of saying our shortcut would be there, and factor out the actual derivative, you'll again see they're very close to one another. They both have a 2x, they both have an x squared plus 1, but this one has a 3x squared plus 1 that this one is missing. So again, in comparing those two, they're pretty darn close, but they're not quite the same. Okay. So let's take a look back up here at the very beginning. Okay. 2x plus 6 was equal to 2x plus 6. Check. We were good there. Okay. Comparing these two, and actually let me factor out a 2 here. So it's 2 times x, it's 2 times 2x minus 1. Okay. And this is then, well, if I factor out completely here, it's really, what is that? A 4 times x minus 2x minus 1. Okay, so we factor those values. So these only differ by what? 2, by a factor of 2. Okay, so to get from here to here, we need to multiply by 2. I know I'm running out of room there. Sorry about that. Okay, here, what do these only differ by? 6x, right? So they only differ by a 6x. And then here, what do these differ by? This one's got a 3x squared plus 1. This one does not. So if we were to take this, what we want our shortcut to, kind of like the shortcut we want to work, and we multiply it by a 3x squared plus 1, okay, we can then get the actual derivative. So again, in summary, right, our first thing worked out no problem. This little shortcut that saves us from having to actually square things out, just using the basic power rule, it turned out to work out just fine, right? Here, this one, when we took the derivative of this one using the basic power rule, it worked out close to fine, right? But it didn't quite work out. Here, we factored it to 2 times 2x minus 1. Here, and it'll be 4 times 2x minus 1. So we just need to multiply our shortcut times 2 to get there, our actual derivative. Here, for our shortcut, it worked out pretty close as well, right? Except this one was missing a 6x. And then over here, it worked out pretty close as well. All right, but this one was missing that 3x squared plus 1. Okay? So this one was missing a 2. This one was missing a 6x. This one was missing a 3x squared plus 1. Can anyone see where the 6x, so where the 2 comes from, where that 6x comes from, or where the 3x squared plus 1 comes from in our original functions there? What is that? Yes?
The derivative of the value in parentheses.
Yes, it is the derivative of what is inside. It is the derivative of what's inside, right? 2x minus 1, okay? We took its derivative using the power rule, bring the 2 out front, right? The only thing that was missing then was to multiply by the derivative of what was inside. A 2 times 2x minus 1, which then would give us 4, okay? The 4 times 2x minus 1 there. I think, did I make a mistake? I feel like I'm 2 times 2x minus 1. Yeah, so we need to multiply by another 2 there to get the 4 times 2x minus 1. I feel like 8x minus 4. Yeah. I feel like I'm missing something there. But this one, so for sure at least, okay, 2 times the 3x squared plus 1. Again, what's missing from that one? It was another 6x. So multiply by the derivative of what's inside, the 6x there. And same thing here. This one was missing the derivative of x cubed plus x, which is that 3x squared plus 1. Okay, that's what was missing. So, all that to say, okay, the chain rule here. Okay, all that to get to the chain rule here. Okay. And so what we had in these scenarios was a function inside of another function, right? G of x inside of f of x. If we go back to the front real quick to see that, right? Here we had x plus 3 inside a square, right? Here we had 2x minus 1 being squared. Here we had the 3x squared plus 1 being squared. And here we had the x cubed plus x being squared, okay? So all those were functions within other functions. And so that's what the chain rule is used for, to take the derivative of functions inside other functions. Alrighty. So if we've got this setup here, if y is equal to f of u, okay, is a differentiable function of u, and u equals g of x is a differentiable function of x, then we can say y is equal to f of g of x, right? Just you put the g of x in place of the u there, it's f of g of x. That's also going to be a differentiable function of x, and, okay, and so here's the thing right here. The derivative of f of g of x is going to equal f prime of g of x times g prime of x. Okay? So in other words, you take the derivative of the outermost layer first, then leave what's inside, and then multiply it by the derivative of what was inside at the end. Okay? Or in terms of like the y stuff here, y prime is equal to f prime of u times u prime. If you want to leave it using the y stuff that we did right there. Okay. All right, so let's see this in action here. All right, let's see this in action because I think it'll help to see an example of the problem. Okay. So A, we've got f of x equals the quantity 3x minus 2x squared raised to the third power. Could we have taken this derivative? Could we have taken this derivative before today? Yes. Could we have done it as it's currently written? No. What we have to do, multiply it out, right? Cube it out, right? So multiply that by itself 3 times, get that nice polynomial there, and then take the derivative. We can actually take the derivative of this, though, without having to do that. We're going to use the chain rule, okay? We're going to take it step by step. Eventually, you won't need to do these kind of like step-by-step kind of steps, but this is just to help us organize things in preparation, just to kind of get us familiar with it, okay? So what I'm going to do to help us kind of recognize how the chain rule applies here, I'm going to say we're going to make a u here, and we're going to make u equal to the inside function. Okay, like this. U is equal to that inside piece there, the 3x minus 2x squared. Okay? So I can rewrite my f of x here. Okay, I can rewrite that f of x as just like y equals u to the what? To the third, right? U cubed. Okay, so I'm rewriting f of x as just y equals u cubed. So you can kind of think this is like a change of variables maybe or something like that. Okay. When I go to take the derivative of y equal to u cubed, what is the derivative of y? What's the derivative of u cubed going to be? 3u squared. Okay, and then we're going to multiply by the derivative of u here, u prime. Okay, we're going to multiply by the derivative of u prime. Okay, by the chain rule there. Okay. What is u prime? Well, if we know that u is 3x minus 2x squared, what will u prime be? 3 minus 4x. Yeah, just take the derivative of that right-hand side there. Okay. Alrighty. And again, this is from kind of like what we talked about right up here, right? If y is equal to f of u, okay, then y prime is going to be that derivative of the outer function there, so the derivative of something cubed, okay, 3u squared, then times the derivative of u prime, or times the derivative of u, which is u prime. Okay, that's that chain rule. And so there's our u prime. We can substitute that in. There's our u, and so it's going to be just equal to 3 times 3x minus 2x squared, okay, to the second, times 3 minus 4x. Okay, and there's our derivative right there. Okay. Questions on any of that? Questions on any of that? Okay, we'll do another one here. Alrighty. All right, letter B. Now, letter B, y equals the square root of the quantity x squared plus 1. All right. Could we have taken the derivative of that before today? Actually, we could not, and it's because we have the x squared plus 1 in there. Okay, we actually were not able to take this derivative, okay? Not able to. So we're going to do it today, though. All right, so again, we'll rewrite it here. What should our u be in this case? The x squared plus 1. Again, it's like kind of the quantity inside there, so we're going to make the u x squared plus 1. Okay? And I'll go ahead and find u prime, because we know we're going to need that for later. If u is x squared plus 1, again, it's the kind of the thing inside the square root there. What will u prime have to be then? 2x, right? It's just the derivative of both sides there, derivative. But now let's rewrite y in terms of the u. So y is equal to just the square root of u. Okay. But of course, the square root symbol is not very helpful, so we should rewrite that as u to the what power? 1/2. Okay, and now we'll take the derivative. Y prime equals, so the derivative of u to the 1/2 is 1/2 u to the negative 1/2 times u prime. Again, we're using that chain rule here, right? We got a function within a function, so we got to use that chain rule. Okay? So that's what we're going to do here. All right? And now we'll substitute in back in our functions. So u is x squared plus 1 to the negative 1/2 times, and then u prime is the 2x there. we've taken the derivative, but of course this does simplify some, so we could stop here, right? We could stop here and say that's it. Of course, like, you know, the 2 and the 1/2, they'll cancel, and so we can get rid of those if we really wanted to there, and say it's going to be x over, because it was a negative 1/2 there, x over x squared plus 1 to the positive 1/2, if you want to rewrite it in simplified form there too. Okay. Up to you, but it does simplify. Questions on A or B? Keep moving. All right, so letter C. All right. Again, this is one we could not take the derivative of this prior to what we just talked about today. We must use the chain rule here. But before we go about taking the derivative, what might be a good idea to do? I was going to say, let's rewrite this, okay? You could take the derivative as we currently see it. If we take the derivative as we currently see it, what rule are we going to have to use also? Quotient rule, right? So let's try and kind of avoid that, all right, and rewrite it this way. Okay, so rewrite it. Technically here we could use a product rule, but we don't really need to because that -7 is just a coefficient, right? If that were like an x, then we would have to use the, or a t I should say, if that were a t, we would have to use the product rule here. But because it's just a -7, a coefficient, we can kind of just take the derivative all at once here. Okay. What would our u be in this case? What's our inner kind of function? What's the function kind of on the inside? Yeah, 4t minus 1. Very good. And so that makes u prime equal to what value then? Just 4. Okay, very good. And so then we'll rewrite this as y equals -7 times u to the -2. Okay, just using a change of variables there. Replacing that 4t minus 1, our inner kind of function, what we said was equal to u, we replace that with a u. And now we take the derivative. Okay, so it's going to be, let's see here, -2 times -7, positive 14, u to the -3rd, right? Lower the power by 1 there. Times u prime. Don't forget that, times u prime. That's our chain rule right there. Okay? There's the chain rule part. We need to multiply by the derivative of what was inside. And now we'll just resubstitute everything. So it's going to be 14 times 4t minus 1 to the -3 times u prime, which is just a 4. Okay, and there's our derivative. Alrighty. Questions on any of that? Questions on any of that? All good? Okay, so then, letter D. What rule are we going to have to use here when we go to take the derivative? And we're going to have to use the product rule. Okay, have to use the product rule, and there's a chain rule within it, right? Because you can see we have functions being squared here and a function being q. So it's actually like kind of 2 chain rules here. All right. So I'm not going to use u twice. So I'll use like a u and I'll use like a v here. Okay. So we'll say the 5 minus n is that, we'll call that our u. And then we'll say v is going to be, well, what then would v be here? The 3n plus 1, the other function kind of on the inside there. Okay. And so the derivatives of these are easy. U prime is just -1. V prime is just 3. Okay, and we'll say that W then is equal to, and what can I rewrite W as? Using my U's and V's instead now? So now I haven't taken the derivative yet. Just how would I rewrite this function W? U squared times v to the 3rd. Exactly right. Very good. Okay, just a substitution. No derivatives yet. Well, I guess we kind of took the derivatives of u and v. Okay, but now we'll take the derivative. All right, so w prime equals, okay, so we're going to use our product rule here. Okay, it's the 2nd, v to the 3rd, times the derivative of the 1st. The derivative of u squared is 2u times u prime. Okay, remember using the chain rule there, times u prime, plus the first, u squared, times the derivative of the second. What's the derivative of v cubed? 3v squared times v prime. Okay, and now we'll just substitute back in the v's and the u's and u primes and v primes. Okay, substitute back in here. So w prime equals, all right, v cubed is 3n plus 1. And then u is 5 minus n. U prime is negative 1. U is 5 minus n squared times 3 times, and then v is 3n plus 1. Oh goodness, I hope I have enough space. I do. Just barely. There it is. How neat is that? Okay, questions, Simeon?
Is it okay if we just don't use the substitution?
You do not need to use substitution, that's right. Okay. If that, yeah, and we'll do a few without a substitution here in just a second too. But I just wanted to kind of break it down here so you could see, you know, kind of all the moving parts before we start trying to, you know, make it quicker, I guess, or whatever. Okay. All right. Questions on any of that? Questions on any of that? All right. So we're gonna just get on to this next page here, okay, and then this will be it, okay. So we're just doing this one last page here, all right, and then we'll give ourselves a time to get started on the homework and stuff like that, okay. So the next example here, we're asked to find all points in the graph of f of x equal to that, for which f prime of x is equal to 0, and those for which f prime of x does not exist. You'll notice here we have a place to sketch, so let's get our graphing calculators out there and put a little sketch down of what that graph is going to look like. Okay. I don't expect you to graph this by hand, but I do expect you to, you know, be able to analyze and stuff. So go ahead, get a sketch down real quick. I'll give you like 30 seconds or something like that. Get a picture of that graph there in your calculator. Okay. We have 30 more seconds here. Okay, so hopefully you've got a graph that looks something like that. Now, that's f, right? That's the graph of f. And some of us here, maybe all of us, will be able to identify where f prime is 0 and where f prime does not exist simply just by looking at the graph here. So for example, where does it look like f prime of x is equal to 0? For what x value? 0, right? Looks like we have a horizontal tangent line there at 0, right? Looks like it kind of flattens off right there at 0. For what x values does it look like f prime does not exist? Positive 1 or negative 1. And why would we say it does not exist there? A sudden change in slope, right? Sudden change from negative to positive, right? It jumps. It doesn't smoothly transition like it does here, where we have positive slopes, but they're less and less and less positive, and then we go to 0, and now they're negative, negative, more negative, more negative, more negative, but then they go to here and suddenly switch to positive again. That's right. Okay, so good. You guys already know the answer here, but let's go ahead and do it also with our analysis using, you know, calculus and stuff. So if we're given the function here and we want to know when the derivative is 0, what should we probably do to this function? Find the derivative, right? Yeah. So first of all, we need to rewrite it, though, into a format that we are comfortable with. So we'll make it x squared minus 1 to the, what exponent should that be? Well, cube root is 1/3, but then times the 2, it'll be just 2/3. 2/3, yeah. 2 times 1/3 is 2/3. Okay. Now, I'm going to do the derivative here using the chain rule, but without all those crazy substitutions. Maybe this will be more clear. I don't know. We'll see. So, but let's just kind of pause real quick and recognize that this is a chain rule. Why is this a chain rule? We have a function here, x squared minus 1 being raised to the 2/3 power. All right, we cannot easily simplify this, right? I can't like easily square this out and then take the cube root, so I can use like my old derivative rules here. I have to use the chain rule because we have x squared minus 1 inside the parentheses here being raised to the 2/3 power. Okay, so then the derivative, you take the derivative of the outermost layer, right? So the outermost layer here is the what? The 2/3 power. So what's the derivative of something to the 2/3 power? Well, the 2/3 goes out front, leave what's inside, and then, yeah, subtract 1 from your 2/3 power, which is now negative 1/3. And then by the chain rule, we then multiply by the derivative of what's inside, 2x. And there's the derivative. There's the derivative. Okay, there's the derivative. So let me just run through it one more time here, right? We had our original function. It was a x squared minus 1, that quantity raised to the 2/3 power. To take its derivative, we kind of take the derivative of the outermost piece first. Something to the 2/3. What's the derivative of something to the 2/3? 2/3 times that something to the negative 1/3. But then we multiply by the derivative of what's inside. There's the 2x, okay, to finish off taking the full derivative there. And that's the answer. Okay, that's the answer. Of course, we want to figure out when the derivative is 0 and when it does not exist. So let's simplify this sum here. The 2 times the 2/3 will make 4/3. All right, and so let's see here. I think I can rewrite that as 4/3 times x over x squared minus 1 to the positive 1/3. Okay, here's where this algebra manipulation stuff comes in, right? Because we want to sometimes work with things and be able to simplify things nicely. And so if I put that together, then it's going to be 4x over 3 times the cube root of x squared minus 1. Okay, that's supposed to be an x squared minus 1 there. Okay, so there's the derivative maybe written in a more helpful form. And so we'll set that equal to 0. So I'll say f prime of x equals 0 when 4x over 3 times the cube root of x squared minus 1 equals 0. Okay. This derivative will equal 0 when what part of it is equal to 0? Just the 4x, the numerator, right? A fraction, right? This is just, you can think of this really, conceptually like it's a fraction. A fraction can only ever equal 0 when its numerator is 0. So you can just set 4x equal to 0 here and see, aha, x is in fact 0. Okay, f prime of x equals 0 when 4x over that 3 times the cube root of x squared minus 1 equals 0, which is really just when 4x equals 0, so when x equals 0. Okay. Okay. The derivative will not exist when what part of the derivative, well, how can we figure out when the derivative doesn't exist, I guess? When the denominator is what? 0, right. So f prime of x does not exist when I'll just set the denominator equal to 0. So 3 times the cube root of x squared minus 1 equals 0. Okay. So imagine dividing both sides by 3. Okay. How do you get rid of the cube root? Cube both sides, right? Cube both sides there, so we'll cube both sides. 0 cubed is still 0, so we get x squared minus 1 equals 0, which is then x squared equals 1. Square root both sides, and since we're in an equation setting here, we get x equals what? Plus or minus 1, which is exactly what we expected there. So at both positive 1 and negative 1, we'll get 0 in the denominator. The derivative will not exist, and therefore the function is not differentiable, right? Okay, the function is not differentiable when the derivative does not exist. Okay? So there we go. Okay. Nothing too new or crazy there except for the, of course, you know, the fact that we're using the chain rule now. Okay? But now we're mixing it in with other stuff that we know how to do. All right. So let's do these last two here real quick. All right, and then we'll call it quits and get you guys time started on your homework and stuff like that. Okay. So letter A. Okay. Before we go about trying to take the derivative here, as we're asked to do, we should probably rewrite it. I'm going to rewrite this as 5x over x squared plus 4 to the negative 1/2. Okay. Oh, negative 1/2. Sorry, positive 1/2. Right, because I left it in the denominator there, so it's still positive 1/2. Right. So if I leave my function in this format, I will have to use what rule? Quotient rule. Okay. Or if you don't like the quotient rule, I could leave it as x squared plus 4 to the negative 1/2. And now I could use the what? Product rule. So it's really up to you, whatever you're most comfortable with. Do you prefer the quotient rule? Do you prefer the product rule? Okay. Whichever one you prefer, go with it. You should end up with an equivalent answer. It may not look the same, but it will be equivalent. I'm going to use, I'll use the product rule for this one, and then because we're going to have a quotient rule in the next one. So I'll use the product rule for this one. Okay. All right, so again, when we take the derivative here, using the product rule, and you see we're going to have a chain rule in here as well, because again, we have a function raised to an exponent here, function raised to an exponent, so we're going to have to use that chain rule too. Okay, so it'll be the second x squared plus 4 to the negative 1/2 times the derivative of the first, so it's just times 5. Okay, so it's this times the derivative of this plus the first 5x times the derivative of the second. Okay, so what would the derivative? Anyone and a brave soul here want to tell me what the derivative of this will be? Let me do it. So Clayton, you want to give it a try? Okay, what do you say?
So 1/2.
So negative 1/2 goes out front. What's going to be inside the parentheses here?
Do I take the derivative of the parentheses? Or
Not yet.
Do I just leave it?
So we'll leave it x squared plus 4. What's the new exponent going to be?
Negative 3/2.
Negative 3/2 times, now times the derivative of what's inside.
So 2x.
2x. And there it is. Okay, there's the derivative using the product rule. Okay, so again, one more thing. I'll just go through it once more here. The second, x squared plus 4 to the negative 1/2 times the derivative of the first, 5, plus the first times the derivative of the second thing, chain rule here. Negative 1/2 out front. X squared plus 4 stays inside the same. Lower the power by 1, and then multiply by the derivative of what's inside there. Gets your derivative. Okay? Questions on any of that? I'm not worried about simplifying for right now. All right. G of t. So we'll do the derivative here of this thing. So what's our outermost function here? What's the outermost kind of layer? E. Okay? So this is essentially like taking the derivative of E. So when we go and take the derivative here, it'll be g prime of t equals, what's the derivative of e to the something? E to that something again. So the derivative here is going to have that e to the 3t minus 1 over the t squared plus 3. Okay, and its exponent. But then by the chain rule, we have to multiply by the derivative of what? Of what's inside here. Okay, we have to multiply by the derivative of what's inside. So we have to multiply by the derivative of this, and in order to take the derivative of what's inside, we have to use the what? The quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And that is your derivative. Okay, that's it. So let me kind of like describe things here. You know, I just want to maybe like take one step back, right? So things now that you're going to see, maybe. Okay? Something like this. F of x equals x squared to the fourth. Did we need the chain rule in order to take the derivative of this in the past? No. How could we rewrite this? X to the 8th, because you multiply when you have a power raised to a power there. And so then its derivative would be f prime of x, which is equal to 8x to the 7th, right? But with the way it was first written there, could we have used the chain rule? Yes, we could have, okay? The inner function is x squared. The outermost function is to the 4th power. So if I want to take the derivative using the chain rule here, it would be, what's the derivative of something to the 4th? 4 times that something to the 3rd times the derivative of what's inside, right? What's the derivative of x squared? 2x. Are these two things the same? Well, 2 times 4 is 8. X squared cubed, x to the 6th. But then times that x, it's going to give us 8x to the 7th. And so they do end up being the same thing here. So if you look at this and you use the chain rule, that's fine. Do it. Okay? Do you need to? No. You could have made it x to the 8th and then taken the derivative. But if you want to use a chain rule there, feel free. It does work. It does work. Okay? All right. Let's get you guys started on your assignment. It is on the Google Classroom right now. You have a good, 20 minutes to work on that sum. And I'll be happy to come around and help you with any questions you might have or that you will have, some, for sure. As soon as I get this stopped here. Please, please, please get started on this here in class.
So, Mark, do you think you have time to find that?
Yes, I can do that here in a second.